So hi everyone, sorry for the delay. Macs and PowerPoint don't go well together, I guess. So welcome to ScalaUA. I'm really happy to be here. My name is Alon Muchnick. I'm a team lead for Wix.com. And today we're going to talk about Scala and the JVM bytecode it produces. First, I'd like to start that if you are interested into functional programming and Scala, you should check all meetups that's going on inside the Wix offices. We're always looking for good engineers, so pay attention for that as well. So what is actually bytecode, and how does features in Scala that do not exist on the JVM, on Java, sorry, are actually implemented? We all use objects, lazy definitions, values. We pass functions as values to other values, and we do a bunch of cool stuff that are not supported by Java. And today, we're going to look at how this actually can be accomplished on top of the JVM. We're going to see how does a class file looks like. How does the bytecode it contains get executed on top of the JVM. And we're going to see how the previous Scala features I mentioned earlier are implemented. So let's get started with a small introduction to bytecode. What is bytecode, and is there such a thing as Scala bytecode? Well, actually, there is no such a thing as Scala bytecode. There is only bytecode. Just the same way as the Java compiler produces class files from Java source code, the Scala compiler, Scala C, produces class files from Scala source code. At the end, it's all about classes for the JVM. The JVM itself is agnostic to the language that produces the source, the class files. So, what is actually bytecode, most specifically? It's a set of low-level instructions to be executed by the JVM. There are about 200 of those instructions. Each one is from 1 to 2 bytes in size. I add, AA load, AA store are just a few of those instructions. To compute the instructions we saw before, the JVM employs an assembly-like register and stack. There are two stacks. We have the local stacks for variables and the operand stack for value of fields, functions, of binary operations, and such as. Okay, the tools we are going to use in this session to see what's going on under the hood and actually disassemble and look inside the engine are Scala C, to see all the compiler phases that are happening during the compilation and the production of the class files, and Java P to disassemble the class file and look at its signature and structure. If you ever felt angry about the Scala compiler and felt it takes so much time to execute, well, you shouldn't have, because it does a lot of stuff for you. It actually does a list of 25 things for you in order to compile your source code. Those things, those steps are broken into phases, and they are called the phases of the compiler. So if you ever would like to see all the stuff that's going on, you can run Scala C minus X show phrases, and you will get a list of 25 steps. Each one contains the step name and a small description of what it does to your code. I would just like to go over like 3 or 4 of those that will be relevant to the future examples we're going to see in this lecture. So we're going to start with the parser, which parses your source code into ASTs, abstract syntax trees. The typer, which add types to your code. Super accessors, which add super accessors to traits and nested classes. Uncarry, which can translate function values to anonymous classes. Lazy vals and constructors, which can move field definition into constructors. And finally, number 24, JVM, where your bytecode is actually being produced. So let's take a small example of only 2 of those phases, just to get a hang of how it actually looks like. So if we have a small, simple class foo with some variables I, j, and k, and a simple function wibble that does a for comprehension and yields c times 2 for c until k. After the parser phase, which is the first one, you can see some differences now. You can notice that the class is now inside the package empty, which we did not declare, which we did not add before. You can see a method init that acts like a pseudo constructor has been added. The plus operation was assigned to k has been expanded to a method $+. And the for comprehension of Weeble have been expanded to a map call. So this is after phase number 1. After phase number 4, where the typer does his thing, we can now see the types have been added to the previous code. You can notice all the ints and strings that suddenly appear inside that class. We can also see that syntactic methods added to access the value of I, j, and k. You can see them def I, def j, and def k. Those were just 2 examples out of the 25 phases that's going on inside the compilation process. In the end, the compiler will do its thing, and a class file will be created. So if we take another example, class regular polygon, which takes a num side inside its constructor, and it has one function get perimeter, which multiplies the side length with number of sides. And we would run this command on it, Java -p -v regular polygon. The -p -v flags will generate an output that is more verbose, plus you will see all the private implementations as well. So we got this huge file, this is not even the entire file, which is our class file. Every class file in Java on top of the JVM has the same structure. Let's go over it quickly. We have the system info, which contains some metadata about the class itself, when it was changed, how many bytes it has, and so on. We have the class file format version, nothing interesting, and we have something called the constant pool, this awful, dragged, huge part of code. What does it actually mean, and what does it contain? So, a bit of background. The development cycle in C++ always involves compilation and linkage stages. The development cycle for Java skips an explicit linkage stage because linkage happens at runtime. When a method or a field is referred to, the JVM searches the actual address of the method or field using the runtime constant pool. It is actually a table of all references needed by the linker. It contains entries of different types, and I'm going to see it later on. Let's try and explain only one record of this huge blob. So let's say that our class is using a constant int. Let's say val x equals integer 365, which is always the same value. Its bytecode representation will look like something x030001 What does it mean? If we would look at the output, Java P will output us, it will look like number 14 or pound 14 equals integer 365. Well, the explanation for the output on the right and the original source on the left is as follows. The first byte of every entry is a numeric tag indicating the type of the entry. The remaining bytes provide information about the value of the entry and rules to interpret its value and content. So if the 14th record inside the constant pool will be the line we are seeing on the left, Java P will output the thing on the right. And it does that because the first value, byte x3, is actually equals to a constant in the JVM called constant integer. That's why it is moved to be an integer. This informs the linker that the next 4 bytes that we have there will contain the value of the integer. That means if we transform 365 into the hexadecimal representation, it will actually be equal to x16d. So if we will have the same example, but only now with a constant string from the function that we saw, let's say calculating perimeter, In constant pool, we will see two lines for it. One is UTF and one is string. The types that, if we saw before that the type of the integer was constant integer, this time it's constant string and constant UTF-8. The entry of type constant string contains a reference constant UTF-8 entry. The entry of type constant UTF-8 actually contains the values. So here we saw just two examples of the many types that can be supported on the JVM and are represented by the constant pool. More complex object will have even more representation and reference to in the constant pool itself. But it's always the same structure. The first byte indicate the type, the rest of the byte indicate the value and how to parse it to actually interpret the value. So if we continue looking at the class file, we see we have three more sections. The first one is the field table that contains information about each field defined in the class. These are references to constant pool entries that describe the field's name and type, as well as access control flags and other relevant data. In a similar way, we have another section called method table, which contains also name and type. However, it also contains, for non-abstract method, the actual bytecode that should be executed in order to achieve the runtime of these methods. Let's zoom in on one function, getPerimeter, the one that you saw before. So finally now we're going to see the instruction set this function runs in getPerimeter. Each instruction starts with one bytecode identifying the JVM instruction, followed by 0 more instructions to be operated on, depending on the format of the specific instruction. These are typically either constant values or reference into the constant pool. JavaP helps us to translate the output into more of a human readable form, displaying the offset or position of the first byte, and the name of the instruction in its human name, and the value to be operated on, if any. Note that operators that contain the pound sign, like number like 23 or stuff, or pound 23 or pound 25, are actually referenced to entries in the constant pool. So if we take this function and we zoom even further on just one line and try to see what's going on, we're going to see that each method call must be able to run it on its own context, which includes things such as locally declared variables or arguments that being passed to the method. This combined makes up something called a stack frame. Upon invocation of a method, a new frame is created on top of the call stack. A stack frame includes always the operand stack we saw before and the local variable table. Let's see a demo, a more graphic run, of what happens when we try to run just the first line that you saw that does the demultiplication. We see it's going to use 4 or 5 instructions: deload, aload, invoke virtual, I2D, and demul. I'm shortly going to explain what does each instruction do. So deload pushes the object reference from slot 1 to the local variable table onto the operand stack. Aload 0 pushes the object reference at slot 0 of the local variable onto the operand stack. Invoke virtual 31, which execute the instant method numSide, pops the operands of the stack to identify from what class it must call the method. Once the method returns, its result is pushed back onto the stack. In this case, the value returned is an integer format, so it must be converted to a double before we can do the multiplication. I2D pops the integer of the value, converts to a floating point, and pushes it back on the stack. And demul pops these two values from the stack, performing floating point multiplication, and pushes the result back on the stack. So after this tedious introduction, now that we actually understand what's going on behind the scene when we compile our code, and we know how to read the bytecode that is generated, and we know the flow of the operand stacks, we can now do something a bit more fun and actually look at all the Scala features I've mentioned earlier and see how they are implemented on the JVM. So we're going to start with a simple class. we have the same class implemented both in Java and in Scala. If you compile this class into a class file, if you compile this source code into class files and run Java P on it to see the output, we will discover several differences. The first one is the Scala class is public by default. It implements Scala object in addition to extending Java lang object. The Scala constructor is created and is public by default. The Java class main method must be declared static. If we see another example, class person, which has only one value, name string, implemented in Scala, and we would run Scala C, Java P on it, we will see several things that were added for us. We can see that for each method in the Scala class, this time it's only name, a field and its getter method are generated. The field is private and final while the method is public. This is the first thing you notice when you start to use Scala, that you don't have to implement getters and setters. The compiler does it for you, and this is the exact example how does it do that. So if we would replace the val that we saw earlier with a var, several things will happen. The field's final modifier is dropped because now it's actually a var, so we can set its value, and a setter method is added for us. If any val or var is defined inside the class body, then the corresponding private field and accessor methods are created and initialized appropriately upon the construction. If we would look at objects, let's say we have an object and it has one value, home, dir. And we will examine the class file that will be created. We will notice that two class files will be created now, config class and config $. This is the way objects are implemented on. So the config class is just a decorator for the synthetic config $. Class that were added for us. It embeds the singleton functionality. The config $. Class actually consists the logic of the method. It consists of the following. The synthetic variable model $, through which other objects access this singleton object on top. The static initializer, also known as the class initializer, and the private method config $, used to initialize model $, and set its field to different values, to default values. It also has getter method for the static field home dir. In this case, it's just one method. If a singleton or an object will contain more additional fields, it will have more getters as well as setters for mutable fields, like if we would use var. So traits, what happens inside of traits? If we have a trait and it has two functions, is similar and is not similar. Again, two classes will be created under the hood, Similarity and Similarity $. Class. Well, we all know traits are just interfaces in Java. At least we think we are only interfaces in Java. The Similarity class is the interface declaring both methods, and it's just a regular Java interface. Similarity $. Class provides the default implementation. When a class implements this trait, the call method is not similar that we saw before. The Scala Compiler generates the bytecode instruction invoke static to call the static method provided by the accompanying class. We can see that call to is similar on line 2 and the jump conditions 7 and 10 to achieve the not logic operation. So in line 2 we actually see invoke virtual number 13. And if you remember how we started, number 13 is a reference to the is similar method in the constant pool. Another thing we have in Scala is a class extending multiple traits. So if we have several multiplication traits like additional, division, multiplication, and subtraction, we would like to have a class that extends all of them. Basic calculator extends all this operation that we saw before. So what does the compiler do? It will actually generate two files for each of the traits. Here we are looking at the addition the addition trait that we've been added, and the addition operation with the public interface. This is their upper class. And we have the actual implementation, the addition operation dollar class, which contains the implementations. Okay, so this is the basic calculator when it extends everything, and you can see several things. Our class will implement every interface and will delegate each method of the corresponding static method inside the abstract class, and you can notice all the dollars delegating to the synthetic classes that we saw before. So every time with the public class tries to delegate something to one of the traits is implementing, you can see is using the static file like multiplication operation, dollar, which means a reference to the synthetic class that's been created. So another thing that is cool to see, a nice example, is references to a method. Let's say we have a method, the same class as from before, and it has a method m. And we can reference by several things, starting from a val, a var, and a def. So how are each of these references for m are constructed? And when does m get executed each time? Let's examine the class file and see what's going on. So this is the class file for the previous. This is the class file for the previous Scala file we saw before. And we can see here lots of information. Let's take a moment and take a higher look. So on the top, we have the constant pool that we all know and love by now, hopefully. On the left, we can see the definitions and bytecode for m, m1, m2. And on the right, you can see m3 and the actual constructor code for person class. In the constructor, in the constant pool, we see that the reference to method m is stored at index number 30. So the third line is index number 30 is a reference to the person method. In the constructor code, we see that this method is invoked twice during initialization, with the instruction invoke virtual 30 appearing first at byte offset 11 and then at byte offset 19. So 11, we see one call to invoke virtual 30 on the right, and at 19, we see the second one, invoke virtual 30. So in other words, assigning a method to a variable definition with val or var only assigns the result of the method to that variable. It does not run it every time. It just saves the output and put it and assigns it to the value. However, using the keyword def gives us a different result. Rather than fetching the value field to return, the method m3 on the top right also includes the instruction invoke virtual 30. That is, each time this method is called, it calls m over and over and over again, and returns the result of this method. We can also see that methods m1 and m2 are created are simply getters for these variables. In case of var m2, we also see that the setter method, setter m2 equal int, is created, which behaves just like any other setter, overwriting the value of the field. So here we took something pretty similar that we all know, like we all knew the difference between val, var, and def. It's nothing new. But this actually allows us to see the bytecode that corresponds to the behavior that we knew before. That vals and vars never execute the function again and again. It's initialized once and it's saved. And def actually runs the function all over each time. So if we mix it up a bit, and this time add a new reference to the three we saw before, and we add lazy val, m4 equals m, something interesting will happen. In this case, the name lazy is suggested, but the value of field m4 is not calculated until it is needed. The special private method m4 lazy compute is produced to calculate the lazy value, and the field byte bitmap 0 to track its state. So the method m4 checks if the field's value 0 indicating that M4 has not been initialized yet, in which case M4 lazy compute is invoked, populating M4 and returning its value. The private method also sets the value of bitmap 0 to 1. So the next time M4 is called, it will skip invoking the initialization method and instead simply return the value of M4. The bytecode Scala produces is designed to be both effective and thread safe. To be thread safe, the lazy compute method uses the monitor enter, monitor exit pair of instructions. And the method remains effective since we only run it during initialization once. So even if we have to lock it, we only lock it once. And an interesting question is how many lazy values can we have in our class? So we know that only one bit is needed to indicate the state of the lazy value. But what happens if we have more than one lazy? So if there are no more than 32 lazy values, a single int field can track them all. An int has 32 bytes, so we can track 32 lazy definitions. If more than one lazy value is defined in the source code, the above bytecode will be modified by the compiler to implement the bit mask. If more than 32 lazy values, another bit mask will be added, and so on, and so on, and so on. So the last thing we're going to see are functions and how are they implemented on the JVM. So if we have an object, we have several functions working on primitives and ints, such as string, int, double, and long. And we have a concat, some int, some double, some longs, and so on. And we would examine the class file that we produced by the compiler. We're going to see 7 classes. So the first two, basic functions and basic function $, we already know them. They are the classes that will be created because we are using an object on the previous screen, object basic class. The rest of them is something interesting because the compiler will generate a class for each of the functions that we saw. If we would look at the concat function, it is a final class extending abstract function 2 from string to string. We get 2 strings and we output a third string, meaning the first 2 strings are the input and the last one is the output. Notice that the plus operation on a string was replaced with a string builder on the bottom. So if you are still replacing every plus when you're working with string with a string builder, don't do it. The compiler already does it for you a long time ago. The SumInt function is a bit more interesting. This function takes in 2 int and returns another one. And we would expect it to extend abstract function integer, 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 meaning take 2 integer and return a third one. But instead, it does something strange. And it extends something called abstract function, MCIIISP. Well, what the heck does SPIII means? Well, this is actually a reference to something called specialized implementations generated by the Scala Compiler. The MCIISP is the name in the name end is telling us that the function is returning 1 int and receiving 2. Thus, we see the III. Well, what does it actually mean? So, Scala type specialization. It's a feature that allows you to generate separate version of a generic class for primitive types, thus avoiding boxing in most cases and resulting in a really improved performance. The only specialized function are function 0 to function 2. The rest of those functions are not specialized. So if we have a function from an int and a double, like a tuple of int double to a boolean, its signature will look like it will specialize into an abstract function, MCZISP. So why ZI? On the right, you can actually see a table with the Scala values, the Java primitive, and the type character. And if we would run a decompiler on the actual function 2 Scala provided to us by Scala, we're going to see a huge class, a really huge class with all the permutation available from double to an int, from a boolean to an int to a string, and so on and so on. And the list goes on forever. This actually allows us, the compiler, to give us better performance when we have function dealing with primitives. So partially applied functions. In Scala, it's possible to create new functions by passing list parameters to existing functions. So if you would call concat with one parameter and two placeholders, it will get the hello function, which is a string to string. If we would do the same with hello and place another placeholder and a value, we will get a function hello xbang, which its signature is only from a string to a string. So how does the Scala compiler support this feature? The compiler will generate a new class for each function that we create with this technique. So this is our concat function after it's been decompiled, the original one. And this is the hello function, the one that we pass two placeholders to it. You can see that internally we are calling concat, only now we are passing a few of the hello object the hello string that we got before and two placeholders, object x and object x2. And this is the hello xbang function, the one that we used hello for. It does the same thing. It calls internally the hello function, but this time it uses one placeholder and one string. So function as a value. If we would like to, the Scala compiler allows us to treat classes as first-class citizens. We can pass them around as values to other functions. And if we would look at the printer class, which takes an input, which is a function output from string to unit, and we see the classes that are being generated, we're going to see again 4 classes. Again, hello class and hello dollar class are not that interesting because we are using object here. The hello dollar anonymous function is the one that we're going to talk about, and a bit about the printer class. So again, this is the hello function. It is just a wrapper for the main method simply called hello dollar, as we saw before. This is the hello dollar class, and it contains the real implementation of the main method. This method creates a new printer. It then creates a hello dollar anonymous function, which contains our anonymous function s2$ that we passed in the beginning as the input. The printer is initialized with this object as the output field. This field is then loaded onto the stack and executed with both operand hello. So if you look at the hello $$ function, which is the anonymous function that is being passed to the constructor, we can see again that it extends Scala function 1, implementing the apply method. It actually creates 2 apply methods, one wrapping the other, which together perform type checking that it is a string in the beginning, and execute the anonymous function printing the input value into println. Looking back at the hello $ main method above, we can see that at the offset 21, execution of the anonymous function, it is triggered to a call to its apply object method. At number 21 here, we see invoke interface 34, which under the hood actually goes to the anonymous function implementation and calls it. And this is the printer class. So we can see that anonymous function here are treated just like any val or variables. It is stored in the class field output, and the getter output is created. The only difference is that the variable must now implement the Scala interface function 1. So we saw a bunch of examples during the last 35 minutes. And conclusions. Well, we've seen how Scala compilers compile several implicit and functional programming features into sophisticated Java bytecode structures. We also saw the tools we can use each time to really go under the hood and observe what's going on. We can see the same pattern starting to happen again and again. When you're using object or function, basically the Scala compiler creates different classes. And they behave in the same structure, delegating to anonymous function, to anonymous classes, and so on. There are many more features that I did not show, hopefully because it was quite tedious. And you can use the tools that we just saw and go and explore every structure, every option you can just implement on Scala, run the tools that we saw, and using this lecture, like try and understand what's starting to going on under the hood. And it's really fun. Like if you ever wondered how does a specific feature is implemented, just run a few commands, get the output, start debugging it, and you will get the hang of it. Those are other great references that will be online for the lecture and other advanced topic on regarding class files, the JVM, and so on. You are welcome to explore it. And thank you. Have a great time here. Questions?
Does JVM acquires monitor every time it assess lazy wall? Yes.
No, only during the initialization, because then it will only check the bitmap 0, and if it's already set, then it doesn't require the monitor. So it's only done once during the initialization. By the way, lazy and Scala is a huge topic, and there are like tons of posts on Stack Overflow. Is it efficient? Is it not efficient? And the implementation has changed like 3 or 4 times during all the last years. So hopefully what I'm saying is true for Scala 2.11. Maybe in new version it change or something like this.
Yeah, I want to follow up on that. Like, so that was for 2.11, right? So
sorry?
That was for 2.11.
Yeah, 2.11,
okay,
exactly.
And why didn't you do that for 2.12?
Because I had 2.11 installed on my computer.
Okay.
Nothing special.
They definitely changed something.
Okay, maybe I'll do a follow-up and see all the differences and stuff like that.
And another question is, so you use Java P for doing that stuff. Is there any other tools you can recommend to?
Yeah, there's something called JUD. I didn't know this myself, but it's like something way more like with the UI, and basically just type a Java disassembly, and you'll get a bunch of even like sophisticated tools that with UI and GUI, which you can compare stuff and pointers and graphics and stuff like that. But there are several good tools, yeah. Like, but for the basic stuff, Java P is really, really good, and Scala C with all the flags is really cool as well. So just take it out.
Thank you.
You're welcome.
Hello. One question in Java 8, basically we do remember that Oracle introduced a default method in the interface. I'm just curious, for the compiling purposes, is the JVM uses the same, some kind of native support of default methods, or it's also generates separate like an interface or class? And if so, why
I would definitely think it, I did not check it with Java 8, but I would definitely think that the implementation would have changed. But again, I didn't check it, I don't want to know, but my logic says then yes.
Okay. Okay, I see, thanks.
Great. Bye guys. Thank you.